Hello, everyone. Can everyone hear me? Okay. I'll probably wait a bit longer for people to show up, but we can get started pretty soon. Okay, I'll wait probably 2 more minutes to start the class. I think today it'll just be me. We won't have a TA. So if you have any questions, just ask me in the chat. I will try to answer them. And also that means that I will please ask everyone to be respectful, not just of me as the only instructor here today, but also of everyone else in the class. You know, if you send too many messages at once, or if you spam or send useless things, it clogs up my chat and I can't see everyone's questions. So please do your best to at least stay respectful of your peers. Don't spam, just ask questions if you have any. That's perfectly fine. I will try my best to answer them. And we can start our class pretty soon. So today's class is going to be on series and sequences. I think Naveen was probably supposed to teach this class, but he has something to do. So I will be your substitute teacher for today. And this is my first fundamentals class, so I apologize if my teaching style or content is a bit different, or if maybe it's a bit too hard or too easy, but I'll do my best to cover everything you need to know about sequences and series, because it is a topic you will see in your pre-calculus classes in school, and also it's pretty important for competitions and also for your future studies in math, including calculus, analysis, and so on. So it's a pretty important topic, and it's what we'll be talking about today. So let's first start off by defining what a sequence is. So in my opinion, a sequence should be a collection of enumerated objects. So I'll give you an example first. Let's say, look at the numbers 1, 2, 3, 4, 5. Okay. Eric, please don't spam the chat. So anyways, essentially, this is what a sequence would be. It is a collection of objects. So definition, I would say it is a collection of enumerated objects. I'll get to what that means in a second. Enumerated objects with order. So for instance, the sequence 1, 2, 3, 4, 5 is going to be different from the sequence 5, 4, 3, 2, 1. Even though they consist of the same numbers, it's only because their order is different that they are different sequences. And what enumerated means is that I can say, let's look at this sequence right here that I'm underlining. I can say, hey, the third number in this sequence is the number 3. Or in this sequence over here, the second number in the sequence is going to be the number 4. So that's what enumerated means. It means that I can put an index on each of these numbers. For example, this is the first number, the second number, the third, fourth, and fifth. And over here, 5 is the first number, 4 is the second, 3 is the third, fourth, and then fifth, and so on. And so that is what I would consider the definition of a sequence to be. And sequences can follow many rules, which we'll talk about in a moment. And they have a lot of properties as well that make them very interesting. So let's see. I'm going to talk about finite versus infinite sequences. This is also pronounced finite. I don't know what's the correct pronunciation. So finite versus infinite. Essentially, a finite sequence is a sequence where the number of terms, for example, here we have 5 terms, it's a finite number. Versus an infinite sequence would have an infinite number of numbers. So the number of terms in the sequence we say is the length. So in the sequence, let's say 1, 3, 5, 7, 9, 11, this has a length of 6, and we can classify this as a finite sequence. But on the other hand, if we were to continue this and list all the odd numbers and say this continued forever, the length would be infinite, and we'd say it's an infinite sequence. So there is a difference between these two, and we'll talk about more properties regarding these. So what I would like to talk about now is going to be would be our properties and how we write and denote sequences primarily. So the notation we use for sequences usually is we're going to write a curly braces, and then we're going to write the number, the variable a, which will represent the terms in our sequences, with the subscript n, which is going to be our index. So n is the index, meaning that is the enumeration. For example, here, the index of 4 is 4. So n is the index, and we can state how long the sequence is. We can say this n, the index, maybe starts from 0 and goes to some number big N. Or for an infinite sequence, so this is a finite one with n, this has a length n plus 1, versus an infinite sequence would be an, n equals 0 all the way to infinity. So that's how we would write an infinite sequence. And we can write, let's say an is equal to 2. That would mean all the terms in this sequence would be just 2s. And there would be n plus 1 2s, because the length of this sequence goes from 0 to n. So that's n plus 1 items in the sequence. So another property of sequences is that if we manipulate 2 or more different sequences together, it will produce another sequence as long as we keep the terms together. For example, what I mean is if we have the sequence 1, 1, 1, 1, and then 1, 3, 5, 7, if we were to add these two, we would get 2, 4, 6, 8. And then this is another sequence. And if we multiply them, it would be a sequence as well, even if these are other numbers. So in general, if we have two sequences, an, so I'm not going to write the indexes here, but this is just a sequence in general, and a sequence bn, and these two are the same length. Then if we take a function, some function f, for example, that takes inputs of an and then an input of bn and outputs some value, then this actually forms another sequence cn of the same length, where each of these function values are equal to cn. So in this case, the function that we did here would just be addition. It would just be f of a and bn would be equal to an plus bn. So that's an example of a possible function. So essentially what I'm trying to say is that if we like mix and match, if we add, multiply, subtract, divide sequences, they'll produce other sequences that are still enumerated collections of objects with order. So these would be the general properties you would see about sequences. And let's talk about some specific popular sequences now. So the first one we'll talk about is an arithmetic sequence. So an arithmetic sequence is going to be something that looks like 2, 4, 6, 8, 10. And if I told you to predict the next number in the sequence, what would you predict the number to be? Well, you would see a pattern in this sequence. Each time we move to the next term, it would be we add 2. So the sums of different sequences, yes, they will be another sequence as long as you keep adding them like with the proper index. If you add the same indexes and it's the same length sequence, you will get another sequence. So sequences are very flexible kind of collection type objects. So let's talk about arithmetic sequences. So in this case, the pattern here is from 2 to 4, we add 2, 4 to 6, we add 2, 6 to 8, we add 2, 8 to 10, we add 2. And so you would guess that the next one would be 10 plus 2, and as many of you said, it would be 12. And that is correct. The next one would be 14, 16, and so on. And so the real trick and the common factor that connects all of these items in our sequence is the fact that each time we move to the next index, we are adding 2 to it. So now let's talk in terms of variables. If we have a starting term, A0, right? And each time we add the number k, for example. So k is going to be some constant number, 3, 5, whatever. If we add the number k each time, we're going to produce the sequence starting from A0, and then A0 plus k, A0 plus 2k, A0 plus 3k, and so on. And essentially, this is what our arithmetic sequence is. Okay. Hello, everyone that just came into the class. Sorry, I did not see that you were all waiting, but we're currently talking about arithmetic sequences, and I have an example of a sequence written here in terms of variables with common adding value k and a starting value of A0. And so we're going to talk about how we can write this in terms of a closed form. So what is a closed form? A closed form is essentially an explicit formula for a specific value in a sequence. So for example, this we can say is the 0th value. This is the first, second, third, based on indexes. So this is like A1, A2, A3. And you can see there's a connection here. For A1, the coefficient on k is the number 1. For A2, the coefficient on k is 2. 3 is 3 as well. And we can see that so if this goes on at the nth term in the sequence, an, we should have the value A0 plus n times k. And so this gives us a general explicit formula for the nth term in an arithmetic sequence. And we can write this formally in mathematics like this. So we say there's a sequence an starting from n equals 0 to some, we can either make it finite or infinite. So let's just do infinite for now. An infinite arithmetic sequence where each term an can be written as A0 plus n times k for some A0 and some value k. So this is going to be our closed form for an arithmetic sequence. And I think what's really neat about this closed form is that you might check that this actually resembles the classic linear equation that you see in Algebra 1, y equals mx plus b. So m is the slope and b is the y-intercept here. And this looks a lot like it because they really are just the same thing. And I'll show you. So if we have an x and y axis here, if we start off giving x as like the n values, we start off at n equals 0, so x equals 0. That would just be A0 as the value in our sequence. So let's say that's around here, A0. And then every time, this is 1, every time we just add k to the value. So the height difference here, like the increment, the slope is just k for every time we increment our index, n, or in this case, x. So in the end, we just produce a straight line because it's growing at a linear rate. So this equation has the equation y equals, and the slope would be k, so kx, and the y-intercept is A0. So y equals kx plus A0 is going to be the linear equation corresponding to our arithmetic sequence. And in general, we can generalize this by saying that there's a function f of x equals kx plus A0. This is just our line. We can say that our sequence is described by this function where the domain, if you remember, the domain is the input into our function, is going to be the natural numbers and 0. So just whole numbers that are non-negative. So 0, 1, 2, 3, so on. This is going to be the domain for a function. And this function is going to describe our sequence. So in reality, we can actually just write this. N equals 0 to infinity. And then an is just equal to f of n. So essentially, we took a function and we classified our sequence with the function. So if you have any questions about what an arithmetic sequence is and how it works, ask me. We're about to demonstrate a neat property, and then we're going to solve a problem with it. So as for the proof of this property, you'll probably understand it more when we talk about series in a bit. But for now, I'll just tell you exactly what this is. It's going to be that the average value in a finite arithmetic sequence is going to be the median of the sequence. And so let's just verify this real quick. If we have the numbers 1, 3, 5, 7, 9, the median we know is 5, right? This is the median. And the average is going to be, if you were to add this up, should be 25 over 5 equals 5. And that is correct. And you can see that this is true because if we were to pair 1 and 9, that would be 2 times the median. 3 and 7 is terms the median, and then there's the median itself. So that would give us a total of 5 times 5 divided by 5 is 5. So that's like a quick intuitive way to understand how this property works. Aggie, please don't spam the chat. If people have questions, I won't be able to see what they're saying, and it's a bit rude and disrespectful to everyone else who's trying to learn. So next, we have an example. I don't know if we usually do contest examples in fundamental classes, but this is a pretty simple problem. I believe it's from AMC 10 from, I think, 2005. You can search it up yourself. But basically what it says is, in the 5-sided star shown, the letters A, B, C, D, and E are replaced by the numbers 3, 5, 6, 7, and 9, although not necessarily in this order. And then we're told that the sums of the numbers at the ends of each line segment, so example AE here, like the line segments AB, BC, CD, DE, and EA, these sums form an arithmetic sequence, and then not necessarily in that order. So they're asking for what the middle term of the arithmetic sequence is going to be. So let's talk about real quick exactly what this line segment stuff means. So for example, the line segment, so it's a certain side, like side AE, it's going to be equal to the sum of the vertices. So for example, sum of the value of AE is going to be the sum of A plus E. So if this is, for example, if A was 3, E was 5, AE would have a value of 8. And we're told that all of these line segments, these sides, they form an arithmetic sequence in some order. And so how do we approach this? We're told to find the middle term, but how are we going to find all the individual terms of the sequence? Well, it turns out that we don't actually have to do that because we're just told to find the middle. And then the middle is the same as our median. So if we're looking for our median value, the middle term of this arithmetic sequence, remember there are 5, so the middle one is the median. The median should just be equal to the average from our property earlier. So the average of the arithmetic sequence. And we know what an average is. An average is just the sum of everything divided by the number of terms in the sequence, which would be 5, because we have 5 sides. So this is a neat formula because we can find what the median value is as long as we know what the sum of all the sides are. And that's really easy to find because we're told that a side is the sum of the vertices. And each vertex, for example, A, contributes to the sum in AE and to AB. And so if each vertex is counted twice in the sums of all the sides, the sum of all the sides, so sum of sides, should just be equal to 2 times the sum of vertices, because each vertex is counted twice. And the sum of vertices is pretty easy to calculate. That's just going to be 3 plus 5 plus 6 plus 7 plus 9, which is equal to 30. So the sum of the sides is 2 times 30, which is 60. And we know that the median, which is the sum over 5, is just 60 over 5, which is equal to 12. So our answer should be D, 12. And this is really nice because we didn't actually have to find out what the actual terms in the sequence was. We simply just took advantage of the properties of an arithmetic sequence, and we used them to our advantage to solve what the median was. And so that's an example of how properties of arithmetic sequences can be convenient. Now, I know there are a lot of other problems in math computations where you don't necessarily use this property, and maybe use some other properties or just some general facts regarding arithmetic sequences. And there are a lot of those, but I decided to show this one because I thought it was a very nice way to demonstrate how properties of these sequences can actually be useful in computations. So let's move on, and we're going to talk about geometric sequences now. So what is a geometric sequence? If I give you the numbers 1, 2, 4, 8, 16, and 32, what would you say the next term would be? Yeah, so it's pretty obvious. The next number is 64. And that's because every time we're moving to the next sequence, we're just multiplying it by 2, right? This is pretty easy to notice as a pattern. So obviously here, we're going to multiply by 2 and get 64. The next one's going to be 128, 256, and so on. So essentially, this is what a geometric series, a geometric sequence is, where essentially between each index, between each term in our sequence, we're multiplying by some common factor. So a common factor, and sometimes it's also called a common ratio. And this common factor is essentially the key to how we're going to express our geometric series. So let's say we start off with the term a0. We're going to use variables now. So with variables, we start with a0, and let's say our common factor is going to be r for ratio. And the next term is going to be a0 times r. So that's a0r. The next one is a0r squared because we're multiplying this term by r. And then if we multiply this term by r, we get a0r cubed, a0r to the fourth, and so on. And if we notice, this is our 0th index term. This is a0. This is a1, a2, a3, and a4. If you notice, a cool pattern that shows up is that whatever index we're on, for example, a2 over here, index of 2, that's the power on our r here. In fact, we can write a0 as r to the 0. So we can generalize this by saying that for some an over here, an should be equal to a0 times r to the power of n. So this is going to be our closed form. And that means we can write our geometric sequence using the braces notation as an, starting from n equals 0. And let's say it's infinite. And each term an is going to be equal to a0 times r to the power of n. And this is a pretty neat representation. And it's cool to note that if r is less than 1, if it's positive and less than 1, then eventually, if we move on forever, like if n goes on and on and on, and it approaches infinity, meaning it becomes arbitrarily large, then this r to the n becomes r to the infinity. And we know that if you multiply a fraction over and over, it approaches 0. So this term approaches 0. So this is going to be more relevant when we talk about convergence later. But for now, I just want to point out that if r is less than 1, it's a common fraction essentially, it'll approach 0 eventually as a sequence. But if r is greater than 1, this will approach infinity because it'll just keep growing and growing and growing. And this is a cool thing we can see when we graph functions, because remember, arithmetic sequences were like linear equations, but over here, the function that properly matches this is going to be an exponential equation. That's because we can write the function f of x equals a0 times r to the power of x. And then our function can be written as an equals f of n for our discrete n integers from 0 all the way to infinity. And if we were to actually plot what f of x looked like, it would look like this. For r less than 1, it would look something like this, start at a0, and then you drop down and you start sloping like that. And then if r is greater than 1, you get that the slope looks something like this. You start off with maybe a0, and then you grow like this. So it's clear that in this case, you just keep growing and growing and growing forever. Well, in this case, you start shrinking towards the y-axis, the x-axis, which would be y equals 0. And we're going to prove this fact later on when we talk about convergence. But for now, let's take it for granted and just assume it's true. And some common geometric series you'll actually see in competitions or problems in general might be the sequence 1, 1/2, 1/4, 1/8, so on, or some other variations, but these are pretty common. You see them a lot. And this is a geometric sequence because the ratio is 1/2 and A0 is 1. And that brings me to my next point, is that a sequence can be defined, like these sequences, mainly arithmetic and geometric, can be defined based off of a starting value. So this is starting value. And then some rule that we follow, which would be multiplying it by this value r each time. And so given a start and a rule to follow, we can generate different types of sequences. And so I'm going to talk about how we usually write this, and it's called recursion. Now, recursion is also a very interesting combinatorial topic, but we'll mainly be talking about the algebraic and just the numerical approach to how recursion works. So I'm going to write a very quick, simple recursion here. How we start this off is by saying A0 is equal to some value. Let's say it's equal to 0 in this case. And then we're going to say AN is equal to, let's say, AN minus 1 plus 1. And then we'll put a brace here to symbolize that they go together. And in this case, this is our starting value. This is our starting case. And we call this formally a base case. So it's a base case of a recursion. And then this is called the recursive relation, and it's going to be our rule. So this is the recursive relation. And it's called a relation because it relates a certain term, AN, to the previous terms, including AN minus 1. So it's relating these. And let's write this out real quick. We start off with 0. And then next one, we add 1 to 0 because remember, A1 is equal to A0 plus 1. That's just 1. We add 1 to this term, we get 2, 3, and so on. And if you notice, hey, this is just an arithmetic sequence. And yes, in this case, this recursive relation resulted in an arithmetic sequence. And in general, if we were to write A0 equals some value, let's say A0, and then AN is equal to AN minus 1 plus K for some common adding value K. This results in A0, A0 plus K, A0 plus 2K, and so on. And this can be written as the general sequence AN, from n equals 0 to infinity, of AN is equal to A0 plus NK. And this is exactly what our arithmetic sequence is. So this recurrence relation generates arithmetic sequences. And that's because each time we're moving to the next value, we're adding a common term K to it. And similarly, if we're multiplying a common term, for example, A0 equals something, AN equals AN minus 1 times some number R, this should result in A0, A0R, because multiplied by R, A0R squared, and this is geometric. So this results in a geometric sequence like this of AN equals A0R to the power of N. If you're confused, just please let me know. I will quickly describe any confusions you may have. But essentially, this is our geometric recurrence relation. And a lot of times when you're learning about series and a teacher wants to teach this to you, they might teach you the recurrence relation first. So they teach you the recurrence relation because they want to show you how we transition from one item in our collection to the next one with the next index. But in this case, I showed you without the recurrence relation. I showed you it afterwards. And I hope it's pretty clear what the recursion actually means. It's just a way to transition between each item in our sequence. And finding the closed form is usually the harder part of handling sequences. You usually know what the relation is pretty obviously, but finding the closed form requires looking at patterns, using different tricks and stuff like that. And this applies especially to series as well. But for now, I'll talk about one more type of recurrence relation. We are given like A0 is some starting value, and then A1 is some other value, and then AN is equal to some function of AN minus 1, and then AN minus 2. This is a function of previous terms. And in many cases where this function is not that nice, this results in very, very complicated recurrence sequences. And these type of recursions usually appear a lot in combinatorial problems. So if you study computer science, or if you just study combinatorics in general, you might encounter a lot of recurrence relationships where the recurrence relation is not very obvious at all. And if you're doing computer science, or if you've just started at your age, there's a technique known as dynamic programming, which is a popular way of handling recurrences efficiently on a computer. So sometimes when you use them, you use inefficient ways to compute these, and the dynamic programming is a technique we use to simplify that. So we have some time. I'll quickly talk about probably the most famous sequence in history, and that would be the Fibonacci sequence. So even if you don't study math, you've probably heard of the Fibonacci sequence. It appears in nature, it appears in problems, it appears everywhere. And that is because it is a sequence defined by the recurrence relationship like this. So you use f to represent it. So f0 is equal to 0, f1 is equal to 1, and then fn is equal to fn minus 1 plus fn minus 2. So this is the Fibonacci recurrence relation. And if we start writing them, we look at 0, 1, and what we're doing each time is we're adding these two. So 0 plus 1 is 1, so the next one is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. Then 8, 13, 21, and so on. And so this is what the Fibonacci sequence is. And unlike previous recurrence relationships and sequences we talked about, the Fibonacci sequence doesn't have a very nice closed form. It does exist, and I'll show you it in a moment. But we can actually have a very easy way of analyzing whether or not the Fibonacci sequence grows at a certain rate. And we're going to make the claim that the Fibonacci sequence grows at most at an exponential rate, meaning that it's at most an exponential speed of growth as we move between indexes. And so we can say the claim. We claim that the Fibonacci number f of n at some index n is always going to be less than equal to some constant c to the power of n, and then c is going to be greater than 1. And this is going to be true for every value of n greater than or equal to 0. And this c is going to be constant. So we want to determine whether or not this constant exists. Is essentially how we're going to prove this. So there's a neat trick in mathematics known as induction. I've talked about it in a previous seminar, and I'm pretty sure that's probably been talked about in other classes as well. But essentially what we're going to do is we're going to say that, hey, let's check this for the base cases. f0 is equal to 0, right? And 0, it is in fact less than c to the power of 0, which is equal to 1. So this is true. F of 1 is equal to 1. And this can be less than equal to c to the power of 1, which is c, because of our assumption here. So it's true for our base case in our recurrence relationship. So now we can prove it's true for all relationships here. So we can assume that it's true up to some value fk. So for all Fibonacci numbers less than fk, less than or equal to fk, this relationship is true. And essentially, if we can prove that these are true, then the next one, fk plus 1, also is true for this. Then we can show that they're all true. So we have a starting point, and we just show that they're all true. So how we do this is we look at the relationships. So let's look at what f of k is, k plus 1 is equal to. This is f of k plus f of k minus 1. And using our hypothesis, which is that all of these below k are true, this should be less than or equal to c to the power of k plus c to the power of k minus 1. And if we can prove that this expression right here is less than or equal to c to the power of k plus 1, then this is less than c to the k plus 1. And this expression here with the Fibonacci numbers is less than c to the k plus 1. And so therefore, f of k plus 1 is less than c to the k plus 1, which is what we're trying to prove. So we just need to prove that this part is true. So we're going to show that there exists c such that c to the k plus c to the k minus 1 less than c to the k plus 1 is true for a value of k. And that's easy because we need to divide by c to the power of k minus 1. And we get c plus 1 is less than equal to c squared. Rearrange this into c squared minus c minus 1 is greater than equal to 0. And this is a quadratic inequality, pretty easy to solve. I'll just do it for you. C is going to be greater than or equal to 1 plus square root of 5 over 2. And this is actually known as the golden ratio, which we write with this Greek letter phi. So this is the golden ratio. And it's because it appears a lot, and you can see it appears here for Fibonacci's as well. So as long as this number C is greater than this, our claim is true. Fibonacci numbers are always less than some number to the power of n. And so I hope this showed you a bit on how Fibonacci numbers are related to golden ratios and how they're bounded by exponential growth. And there's a formula. It's not so easy to prove at all. There's Benet's formula. And it states that the nth Fibonacci number, this is the nth Fibonacci, I was using uppercase N, uppercase F, is going to be equal to this very nasty radical expression. And you might be wondering, how is this going to be an integer, right? Fibonacci numbers are all integers. How is this going to be an integer? Well, that's because if you expand this with binomial expansion, the non-root 5 terms will cancel due to the minus sign and the minus sign over here. And then we'll divide all the root 5s out using this. So it's actually always going to be an integer. So this is a pretty neat formula. It's used occasionally in competitions, but honestly, you don't see it too much. So let's talk about series now. If you have any questions about sequences, I'll give you maybe like 20 seconds to ask while I take a small break. Okay, so is there going to be a TA? No, there will not be a TA. Somehow everyone on the staff team is busy today except for me. So I'm the only one teaching today. How many types of sequences are there? Sequences, there are an infinite number of possible sequences. A sequence is literally any collection of items which can be enumerated and have order. The ones that we've been talking about are just very common sequences you see in mathematics, like arithmetic sequences, geometric ones, Fibonacci's, etc. And but in general, there are so many out there. Many of them don't have any meaning to them. There's no point in studying them. They have absolutely no relation to human life whatsoever. It's pretty much useless. But there are a number of interesting sequences. I believe there is an online sequence or series encyclopedia that lists a lot of different series and then like the numbers, the properties, and stuff like that. But I don't remember the exact link, but you can search it up. A staff, so staff, no, you cannot be a staff. What are TAs? TAs are teaching assistants. It is a common term. It's a common term used in college and camps. It means you're just an assistant who helps the instructor teach a lesson, usually answer questions or provide supplementary help to the students. No shout outs. We're about to begin the lecture again. So series definition. What is a series? So series are actually very, very related to sequences. And that's because a series is literally just a sum of a sequence. So if we have a sequence, let's say 1, 3, 5, 7, 9. This is the sequence of odd numbers, odd positive numbers. Then a series, let's say S of n, is going to be the sum of the first n terms in here. So it's just 1 plus 3 plus 5 plus 7 plus so on until we have n terms. So this is the nth series of this odd number sequence. So we have a sequence an, let's say it's infinite for convenience, starting from 0 all the way to infinity. Then the series of some big N, right? The nth one is going to be equal to, and it's going to be the sum of all n first consecutive terms, so sum of consecutive. So it's going to be A0 plus A1 plus A2 plus all the way to plus an minus 1. And you notice that this has n terms here because we go from 0 to n minus 1. And turns out that there's a very easy way to write series without needing to write like this kind of bracket notation with all the addition signs. We just use something called a summation. So a summation is written like this. So essentially write Sn. This thing is equivalent to, and this is the Greek letter capital sigma. Sigma is like S, so that's why it's related to sum. And we're going to use what is called like a temporary index. So I'll explain what this means in a moment. Temporary index I, starting from 0, going all the way to n of AI. So what does this mean? This means that we are summing all values of AI starting from I equals 0 all the way to n. So that's what we're doing here. We have AI starting from I equals 0, I equals 1, all the way to I equals, well, this should be n minus 1. Actually, apologies. This should be, we're going to write this as n here to keep things consistent. This should be n plus 1 terms, and we're going to have this series mean that we're adding up to the nth value. So in this case, this is not n minus 1. This should just be sum up to n. We're going to add all the AIs from I, starting from 0 all the way to n. So that's what the summation means. It's pretty simple. If you have any questions, ask, because I'm going to talk about some properties and summations real quick. Okay, so I'm going to show a very quick example. Let's say that we have this. Say 2ai plus 3. How can we express this in terms of Sn? It might seem pretty tricky. Like, these are different sequences here. We're talking about the sequence AI here, and talking about the sequence 2ai plus 3 here. So what we're going to do is we're going to say, hey, let's take advantage of some classic addition rules. This is probably associativity, So if we look at the numbers a plus b plus a1 plus b1 plus a2 plus b2, by the associative principle of addition, we can write this as a1 plus a2 plus b1 plus b2. Essentially, we tore apart what's inside of each of these things we're adding, and we group them with themselves. So we group A's with A's, B's with B's. So in this case, we're going to break this apart to 2ai and then 3. So we can write that as this. 2ai plus sum of from n I equals 0 to 3. So in this case, this is how we broke it up using the associative principle. And then also, let's look at this summation here real quick. There's no more dependence on I, so no dependence on I. That means that we're just adding a whole bunch of 3's together. And how many 3's? Well, from 0 to n of them. So that's just n plus 1 3's. So this summation should just be equal to 3 times n plus 1, because we're just adding n plus 1 3's together. So now let's look at this summation right here. By the distributive and factoring principle of addition, we know that, for example, a c plus b c, this is just equal to c times a plus b. We just factor out the common factor of c. So in this case, 2 is a constant. It's in every single term we're adding here. So just pull the 2 out. You can write this sum as 2 times the summation from I equals 0 to n of ai. So essentially, we rewrote this summation here in terms of 2 times, this is going to be s of n plus 3 times n plus 1. So that's a pretty neat trick of why summations are useful. It's useful for simplifying how we write things, how we think, and it can help us organize our thoughts into intuitive decisions that we're doing during math. And let's talk about arithmetic series now. So arithmetic series are just going to be the sums of arithmetic sequences. So say our sequence an is defined by an equals a0 plus nk. And then our series is therefore s of n equals the sum from I equals 0 to n of ai. And then if we substitute this formula here, we're given the closed form of the sequence, right? This is closed form of sequence. We can use this to find the closed form of the series. And we can do this by substituting this in. So we get this is equal to the sum of n I equals 0 of a0 plus nk. And hey, a0 is a constant here. K is a constant. So this is pretty similar to that example I just showed you. We can split this summation apart. So like this, I equals 0 of just a0 plus the sum from I equals 0 to n of n times k. Apologies, this should not be n, this should be I, because there's a formula for ai. So in this case, this should be I times k. And then k is just a common factor that we can factor out of the sum. So this is just equal to, and then remember, this is just a0 times n plus 1, so this is a constant, plus factor out the k times ni equals 0 of I. And all that we need to do now is find out what this summation is. But hey, this is just 0 plus 1 plus 2 plus 3 plus 4, all the way adding up to n. If you ever had any experience with this expression, you know that this is equal to n times n plus 1 over 2. And how we get that, there are two ways to do this usually. One is with induction, the trick I just showed you earlier. You can assume that this formula is true, maybe based off observation, and then prove it using induction. Or you can simply notice a pattern and then pair. So we notice that 0 and n can pair together to add up to n. 1 and n minus 1 add up to n, and we just keep pairing them into sums of n until we're left at the middle terms. So there are two cases. We have an odd case of terms and an even number of terms. And then it turns out that both cases will result in the same formula. So I'm not going to show you explicitly, we're kind of short on time, but it will result in this closed form for this summation. So if you plug that in, you get that a0 n plus 1 plus, and then it'll be kn times n plus 1 over 2. And then let's factor out the n plus 1s. So draw an arrow. Factor out the n plus 1. So n plus 1 times, and then a0 plus kn over 2. Let's turn this into a nicer looking expression. So there's n plus 1 times 2a0 plus kn over 2. So this is going to be our closed form for the series. And it's a bit of a complicated formula to remember, actually. We're just given some very simple sequence values, and we have to know this formula. It's pretty tough. But I'll show you a very cool way you can just remember this without actually memorizing the exact formula. Yeah, please don't spam, guys. It would really help me. It helps your peers as well. So a trapezoid, if you know what a trapezoid is, it looks like this. And if we have a height of h and two bases, base 1 and base 2, the formula for the area of a trapezoid is 1/2 height and then the sum of the bases. So base 1 plus base 2. And if you notice, our sequence, our arithmetic sequence starts off at a0, goes all the way to a0 plus nk for the series of n. And this is a trapezoid as well. If this is our two bases, the sum of our bases, b1 plus b2, is just equal to 2a0 plus nk, because we're just adding these two bases. And then the height, the number of terms in our sequence, is n plus 1. So if we use the trapezoid area formula, we get the area, or the sum of the sequence, the series, is equal to 1/2, and then height is n plus 1, times some of the bases, which is 2a0 plus nk. So it's a lot easier to know this technique rather than memorizing the exact formula. If you're given a sequence of numbers, just simply add up the bases for the starting and end point, the number of terms, and then divide by 2. And that's how I would do it. So if you use this formula, you can easily prove that property we mentioned earlier regarding averages and the median. It's pretty easy to show using this formula. So you can try that out on your own time. Let's quickly talk about geometric series. These are inherently a lot more interesting than arithmetic series. That's because adding these isn't very intuitive in the first place. If we have a sequence a0, a0r, a0r squared, and so on, adding them actually takes a bit of effort. And let's say that we're going to handle a finite series first, so up to a0r to the n. So s of n is equal to, I'm not going to use summations here just to make it look a bit nicer, but it's going to look like this, a0r plus a0r to the n. And then what's neat is that if we look at this series, a0r plus a0r squared plus, and then a0r to the n plus 1, essentially everything is one term ahead. So it corresponds like this. This is just equal to r times s of n, because that's just this sequence multiplied by r. But then they share a lot of common terms. If you notice, a0r is a common term here. a0r squared is a common term. even a0 r to the n is a common term with the value over here. The only ones that are not common terms are a0 and a0 times r to the n plus 1. So if we subtract these, we can get s of n times r minus 1, if we subtract these, is equal to, and all these common terms will cancel out except for these non-common terms. So we get a0r to n plus 1 plus a0. It should be minus a0 minus a0. And if we divide by r minus 1, we get s of n is equal to a0r to the n plus 1 minus a0 over r minus 1. And that's a pretty neat formula. This is going to be our closed form. Closed form. And something I like to talk about more is this trick. This trick is a very useful trick because it's not only used for geometric series. If you've heard of, there's a type of series known as Arithmetico geometric series. And it basically looks like a geometric series, but the coefficient is arithmetic. So it's pretty complicated, but you can search it up. It uses a similar trick, but you use it twice to find the closed form. And it's pretty interesting. So let's talk about infinite geometric series now. And it means that we're looking at s of n as n grows arbitrarily large. In fact, it'll approach infinity, or is what we're saying. I mean, if we look, if r ends up being greater than 1, r to the n plus 1, as n gets super large, becomes infinitely large as well. So this approaches infinity. But if r were less than 1, and like greater than 0, if it's a fraction, as we mentioned earlier, r to the n plus 1, as it goes to infinity, should approach 0. So this term becomes 0, and s of infinity should approach the constant value of negative a0 over r minus 1, which is a0 over 1 minus r. So this is the closed form for an infinite geometric series, and these appear a lot in competitions. So this is very worth memorizing. It's very simple as well. And we can use this as, for an example, 1 plus 1/2 plus 1/4 plus 1/8. If you've ever wondered what this is, if you just keep adding halves over and over and over. If you plug this into the formula, a0, the first term is just 1. So equals 1 over 1 minus, and then the r is our common ratio, our common factor, which is 1/2. This is equal to 2. So bam, we have that this is equal to 2. It's a pretty neat formula, but this won't work at something like 1 plus 2 plus 4 plus that, because when we created this formula, we inherently assumed that r was going to be in this range here. We assumed that it was not going to be greater than 1, or else there's not going to be a converging value. And so this can't be used with this formula. You're not going to have a negative expression. If r equals 1, doesn't it also approach infinity? Yes, you are correct. If r is actually equal to 1, this approaches infinity as well. And that is the case. It has to be strictly less than 1 here for it to approach 0. And we'll talk about this real quick. But first, I'd like to quickly give a shout out to these formulas here. These are pretty useful in, I would say, like the Amy level competitions. If you're there at that level, or you're going to go to that level soon, these are nice formulas to know. These are the sum of squares and the sum of cubes. So these are pretty easy to memorize, so memorize these. But if you're not aiming for all of the problems and these kind of like levels of difficulty, you don't need to worry about memorizing this. It's just something fun to know. And these can be proven using induction or using, there are some very neat tricks that you can search up online. So I have maybe 8 minutes left. I'd like to briefly talk about convergence and divergence. So this is a pretty serious topic because convergence and divergence is something you talk about more in calculus, analysis, and upper levels of mathematics. And it's the sole reason why series are taught in pre-calculus, because everyone wants to prepare you for what you're going to be using them for in calculus. And so what does it mean to converge and what does it mean to diverge? So convergence means that your function or sequence or series will approach a constant value. and then it'll stay there. So it'll stay there. This is a very informal definition, by the way. There are very formal definitions you learn in analysis that I'm not going to explain because they'll revolve around limits. But essentially, this is what it means. It'll approach as you go on in the sequence. So like when you're approaching infinity for n. And then diverge is the opposite of converge. So it does not stay at a value. It does not stay at a value. So let's talk about some examples real quick. Obviously, an arithmetic sequence, a0 plus nk, no matter what k is, unless it's 0, this is going to be divergent because it's never going to stay at a certain value. Your next value is always going to be different than the one before. While for geometric series, a0 times r to the n, I claim that these will converge if your r is less than 1. And we can show that real quick, but first, I want to talk about why it is important to study convergence and divergence. So you might think it's completely irrelevant to what we're talking about besides the fact that we're just looking at convergence and divergence of sequences, but this is not the case. Let me give you an example. We say that x is equal to 1 plus 1 plus 1 plus 1 plus 1, so on. And I say, okay, x is therefore equal to 1 plus, and then if you put parentheses here, this is just itself, so 1 plus x. This will result in, if you subtract x from each side, 0 equals 1. But we know this is blatantly wrong in mathematics. There's no such thing as 0 equals 1. This is a false equivalence. And so what went wrong in our example here? What went wrong was actually that the expression we're handling for x is actually infinite. It diverges. This expression approaches infinity as you keep adding ones. And when you write infinity plus 1 equals infinity, that's basically what we're doing here, you can't subtract infinity off both sides and say 1 is equal to 0. You can't play around with infinity in these kind of scenarios. And that's exactly why it's important to know whether or not some expression is divergent or convergent before you manipulate it. So in this case, if we didn't check the divergence, we would make this wrong assumption and get 0 equals 1. And so we need to know and understand that something is convergent first in order to manipulate it algebraically. And if you notice, we actually did that with our geometric series. You might have taken this for granted, but what I did here, instead of showing the usual way to prove a geometric series that's infinite, you'd usually just manipulate it right off the bat. But without proving it's convergent, that's actually illegal in rigorous mathematics. That's because you don't know it's convergent. It could just be divergent, and you might get in an error, a very, very incorrect formula in closed form. So what I did was I found the finite expression first, and then we analyzed its behavior as this n plus 1 approached infinity. And we said that as it did, if r was in this bounded range here, it would converge to a certain value. And so that's how we handled it for the infinite geometric series. But in general, you want to make sure if you're going to handle something algebraically, you want to make sure it converges first, and then you do it. So that's important. And another common pitfall, I'm going to talk about 2 more common things that people get mixed up about. X plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, so on. If you think about this, if you start off at like 1, subtract 1, that's 0. Add another 1, that's 1. Subtract 1, it's another 0. If you keep this oscillating pattern going on and on and on, you might wonder, what does it go to? It might just keep oscillating forever. But if you use the wrong mathematical manipulation of x is equal to 1 minus x, therefore x is equal to 1/2, basically we put parentheses here, that's what we did. Then, and this would be a minus then, you'd flip all the signs. Then this would tell you that this eventually approaches 1/2. But this is wrong because it keeps oscillating. We know it doesn't stay at a constant value. And we know that this should be a divergent thing. If you actually use calculus and some things, you can show that this is going to be a divergent expression. So someone asked, you can never add, subtract, multiply, or divide by infinity. And generally, I would say you can, but it's only because in those cases, there are limits and calculus operations that are happening behind the scenes that make it work out. For example, when I say 3 divided by infinity approaches 0, this is a true statement, and we're dividing by infinity here. But I have to be very cautious when I make these kind of statements, especially when I'm using unknown variables like x over infinity. I can't necessarily say that this is going to be 0 in case that x actually approaches infinity itself. So in this case, this is wrong. So if you're going to be messing with infinity or very, very large numbers, be careful what you're doing. If you think it logically makes sense, for example, you should know that in this case, it will never actually reach a value of half. It's always going to be oscillating between the integer values of 0 and 1. So this doesn't make sense. In this case, this one does make sense. 3 dividing a large number approaches 0. If you're going to be dividing infinity by numbers are always going to be infinity as well. So these are valid things to assume, because if you take an infinite value divided by something that's finite, you get an infinite value. But what I'm saying is be careful when you do it with algebra, when you're doing it with values of x and y and such, because you don't know whether or not those variables are actually convergent or divergent. We're almost done. I'll try to end it around 4. So let's see. Another common pitfall is, a couple of years ago, it's pretty popular saying that 1 plus 2 plus 3 plus 4 and so on is going to be negative 1/12. And unfortunately, this was a very popular claim, not only among people who don't study math, but also people who actually study math, which is pretty sad when you think about it. This is a strictly positive series. How are you ever going to get something that's negative? It doesn't make sense. But people who don't understand how this negative 1/12 comes might be confused. So this is clearly a divergent sequence. But what happens is, when we study complex analysis, a very complicated topic, there's a function known as the Riemann Zeta function. We got it like this, where this is equal to 1 over 1 to the k plus 1 over 2 to the k plus and so on. And this is defined for k greater than 0. And for these cases, there are always values that correspond to this. However, unfortunately, it should be greater than 1 actually. Unfortunately, there is a misconception, because in complex analysis, there's a thing known as an extension to a function. You can extend a function beyond its normal domain. For example, the domain here would be k is greater than 1. So extend it beyond k is greater than 1, and you create like a mirror function, essentially, like a fake version of the zeta function that exists for k less than or equal to 1. And it happens that zeta of -1, which is going to be equal to this, if you notice, is going to be approaching the value 1 over 1/12 for the extension only. So it became a misconception that this divergent series was actually equal to -1/12. But that's not the case, and you should not assume that it is the case, because you should know that this is divergent using your common sense. So that's a cool story. You guys are free to leave now, but I'll quickly talk about, in maybe 1 minute or so, how we can show that a sequence is divergent or convergent. And one very interesting technique is known as monotonic sequences, or like monotonic increasing or decreasing. So if a sequence or series, each term you add or each term you analyze is increasing or decreasing, you can use that to your advantage to prove something is convergent. So if a sequence or series is monotonically increasing and then bounded above, meaning that you showed that an or Sn is less than some constant value, so it's bounded above, and it's increasing at every term, therefore it must have a convergent value. And the same goes for decreasing. It would be bounded below. Then basically it would be greater than or equal to something. So we can use this for our previous thing. We've been talking about this the entire lesson today. We were talking about a0 times r to the power of n as n approached infinity, right? So if r is less than 1, let's look at this example here. So let's say these are all positive numbers here. a0 and r all positive. So we know that a0 r to the n is always going to be greater than or equal to 0 for every single n value that's greater than 0 or greater than or equal to 0. So it's bounded below. Not only is it bounded below, though, it's decreasing at every single term. Because remember, n plus 1 is just this multiplied by r. And then r is less than 1, so it's a fraction of what it was before. So this is going to be monotonically decreasing. And because it's always decreasing and it's bounded, it's going to converge. And graphically, we can see that. It's bounded below by the the x-axis at y equals 0. And then this exponential function is going to keep decreasing. We can prove it's always decreasing. And therefore, it's going to approach some value above the bounded stuff. For sure, it turns out it's actually just the bound. So that's how we prove that this is a convergent value. So thank you for attending today's lecture. I went a bit over time, but hopefully that's okay with y'all. Thank you for staying and attending. Unfortunately, because this is not my class, I do not have a handout, nor am I planning to write a handout for this class. So you probably have to wait for someone to write out instead of me. But the recording will be posted. I don't know when the staff members will be able to post it. I'm not too good at posting these kind of things, but we'll try to get it up so you can watch it over again. If you have any more questions, feel free to stay and ask. I'll be on for maybe 1 or 2 more minutes, and I'll take some questions if you have any. And thank you for attending. So if you didn't want this call out, I apologize, but Leon, you asked if this function does not work. So essentially what's really happening here is, let's look at the function square root of x, right? Function of square root of x is only defined for x greater than or equal to 0. If we want to define this function so that it covers negative values as well, maybe we'll say that this follows like negative square root of negative x, or like negative square root of negative x. And this will work for x is less than or equal to 0. So this is how we can extend this function to a larger domain. So that's essentially what was happening here with this function, the Riemann Zeta function. And we extended it beyond its normal domain and achieved negative 1/12. But that's not the actual value, because the actual function is not actually defined there. So for example, you can't say that given this, you can't say the square root of like -2, and it's going to be negative root 2. That's just false. So that's basically what happened, if you were still on and still listening. So I think there are no more questions. I'm going to end the lecture now. Thank you for all coming once again. I hope you have a good weekend.